Okay, so sorry about that. I did not set up the audio channel correctly the first time, so now it is actually correct. Anyway, let's go ahead and talk about the solution to this homework assignment. So I am going to write the code to do this. All right, so the first thing we need to do is to download the file, which there's a link here. And we'll save the file to the temp folder. Oh, okay, I guess it put it into my usual folder. That's okay. We'll just make a copy here. And copy over here. All right. So the code here is supposed to, what it's supposed to do is to do the usual division thing. But we also want to turn it into a function and use all the same conventions as all the functions. So before we do it in assembly, let's do it in C first. So the usual code that we use is as long as dividend is greater than or equal to divisor, we perform an iteration of the loop. And in the loop, we say divisor plus, nope, we need a local variable as quotient, u in 8 underscore t, quotient, and quotient needs to be initialized 0 first. And then in the loop, we increment quotient, but we also have to subtract divisor from dividend. There we go. And when this is all done, we got one thing to do. We have to say, do we want to store the remainder? So we have to check whether remainder as a pointer is null or not. If it is not, then whatever it points to, p remainder, is going to be getting the remainder, which is stored in dividend in this case. And the return value of the entire thing is supposed to return the quotient. So I'm going to return quotient here. So this is the C code, and I'm pretty sure this is correct. So just in case, we're going to compile the program just to see whether I made a mistake or not. Nope. So apparently this code is correct. And so now the question is, how do we convert this into assembly code? And then how do we test it? Because I did not tell you how to test it. I did not give you any code to test your program with either, because that's part of the exercise is also to act as the caller to find out whether your program is working or not. So the first thing we do is we copy this program to div_sub.ttpasm just so that we have an assembly version of this. And in this code, we're gonna insert comments to all the lines. And we probably want to have one space there. There we go. So that we have all the comments. I did not modify my VI locally to use syntax highlighting, so that's why it's not showing up. There's no syntax highlighting here. I think that's exactly why, because I did not specify syntax highlighting here, and it doesn't understand what is TTPSM, but that's okay. We can continue with this. So div is the name of the subroutine, so that's why the label has the same name. At the top of the stack, we got p remainder. After that, we have divisor as a parameter. Then we have dividend as a parameter. Those three are the parameters. And then we have the return address. And this is what the stack point is pointing to. So when we get into the subroutine, we first have to kind of retrieve those particular values from the stack. So we use a CPR instruction, CD, so that we copy register D to register C. And then after that, we can use register C to retrieve the dividend and also the divisor. So we use a LD instruction here, LD well, I can put it into A here. Oh, first of all, we have to increment register C. So the C now points to dividend, which is the first parameter. And then we do LD here. So that register A is our dividend. And then we increment C again. So that C is now pointing to divisor. And then we LD B, let's see. So that now B is our divisor. And we can use register C as our quotient. So we do LDI C0, and we'll say, C is our quotient. Okay. So the rest of the code is about the same as before, the loop here. So when we perform the loop, what we do is we do a compare. And first of all, we know that this is the beginning of a loop. So we'll say while begin. And we know that by the end of the loop, we need a while end. So we first define these labels. And because this is also a loop, we have a JMPI instruction that unconditionally will continue execution at the label while begin. Okay, so this is the structure of the loop. And now it's time to specify the compare and the other instructions. So what we're comparing here is we are comparing the dividend, which is in register A, with B, which has the divisor. And if it is less than, and because this is unsigned comparison, we use JCI, jump if and only if the carry flag is set. And in this case, if the dividend is less than the divisor, we actually we want to exit the loop. So JCI is exactly what we want. Quotient plus class is just incrementing register C. And this is just subtracting the dividend, which is in register A. It's subtracting the divisor, which is in register B, from register A, which contains the dividend. There we go. So by the time we get to the exit here, okay, it helps to kind of comment, what we have here. So register A has the remainder. Register B has the divisor, no longer useful to us. And register C has the quotient, which is definitely useful to us. So now we look at this code and go like, okay, we need to return the quotient, so that means we cannot lose the quotient. But we also want to keep the remainder around at least until we know whether P remainder is null or not. So the trick here is to find a place to store the registers, but we don't want to use any static location because that would mean a nested call to this is not going to work. So that means, we really need to use the stack and store these two registers temporarily until they're useful. The first one we store is the dividend, because the dividend won't be, the first one we store is the quotient, because the quotient is not going to be in use anytime soon. So we do a decrement D, which is a reserve room on stack. And then we do a stdc. So we push the value of C, which is our quotient, on stack first, so that it will be retrieved last. And then we decrement D again to reserve more room on stack. And then this time we store register A on stack. So we push A, which is our remainder. Now we have all three registers free again for our use. So in order to perform this comparison, what we need to do is to CPR, CD again, so that we start with the stack pointer. But this time we have to be careful because the stack pointer is not pointing to the return address anymore. It is now pointing to 2 bytes below the return address. So in order to get back to P remainder, which is the last parameter, so let's find out exactly what C is pointing to. C is now pointing to saved remainder, increment C. C now points to saved quotient, increment C. C now points to the return address, increment C. C now points to the dividend. Increment C. C now points to the divisor. Oh, I cannot spell dividend. There we go. And then we increment it one more time, and C now points to P remainder finally. There we go. So when we retrieve that, we are basically using a load instruction to load it into any one of the other two registers. Even loading it back into C is okay because we don't really need it back anymore. So we can load it back into C. Okay. So C is now actually P remainder, which is a pointer itself. Okay, this is not where we want to store. This is pointing to where we want to store the remainder. Okay, so now that we have P remainder, we need another register to compare. So we can use register A. Okay. Now, obviously, these 5 increments, can be combined into LDI A5 and then just add CA. So that would accomplish the same thing. But I really want to use this opportunity to kind of explain what is on the stack as we increment C. So that's why I did it this way. So anyway, here we do a comparison between C and A. And JCI, because we only have JCI, we don't have J and ZI. So JCI, when it is null, we just skip the whole thing and we just say, okay, ta-ta, we are skipping around the entire thing. So we go to, we'll call this else, okay? We'll call this else here, okay? Because at this point, we are not at else, which means P remainder is not null. So if it is not null, we want to store our remainder over there. So what we do is register D is still pointing to the remainder. So this is perfect because now we can just say LD register A is fine. There's no reason why we cannot use A. Okay, so A is the saved remainder. And once we use it, we should increment the stack pointer. So we deallocate stack space for saved remainder. So now register A has the remainder, and register C is in fact the pointer to the remainder. We can do ST instruction using C as to point to the location and A to specify the content. So this is basically storing to P remainder the remainder, which is known to us as the dividend, the leftover part of the dividend. Okay. All right. So, okay. So I can probably do it like this. Okay. Instead of using else, I'm going to change the label to end if. Okay. So by the time we get to end if here, we have to be careful about what the stack pointer is pointing to. The stack pointer is still pointing to the saved remainder. So we need to increment D to deallocate the saved remainder from stack. And then we still have one more item, which is the quotient. Remember, we saved the quotient first. Up here, we saved the quotient first. So the second, at this point, the stack pointer will be pointing to the saved quotient, which means, hey, this is exactly what we want to return. So we need to do LD AD. A is the saved quotient. So now that we pop it from the stack, it is important for us to increment D again, because otherwise D is not going to go back and point to the return address, which is what we need in order to return from the subroutine. So now that D is pointing to the return address, we can now actually perform the return operation and return to the caller operation, not the return value. The return value is taken care of over here. So that is the LDB, okay, BD. B is the return address. increment D. Remember, every time we use something, we consume something from the stack, we have to increase the stack pointer just so that we make sure that that location is no longer allocated. And then the JMPB should return us back to the caller. So this is the subroutine. And obviously, how do we know the subroutine is working or not? Well, let's go ahead and write the main program to test this. So we do LDID with 0 to initialize the stack pointer, and main is here. I put a label main only because I want to make it clear that this is the entry point of the main program. So let's go ahead and find out what we want to do here. So what we want to do is I want a local variable, for instance, to store the remainder. So let's do a uint_t as a local variable, and we'll call this x. Okay, this is just pseudo C code anyway. It's not going to be compiled. But to do this, I need to decrement d. Okay, allocate for x. Okay, and then we can go ahead and perform our well, let's allocate another space here. So and then with this we'll call y. Okay, decrement d, allocate for local variable y. So we got two local variables here, and then I want to specify what I want to do in C first, and then we'll look at how we do it in assembly. So I want x to be div, and let's say the dividend is 7. But in here, I want a nested call so that we have a nested call to div where the dividend is 15 and the divisor is 3, and we want this not to store any remainder. So we put a 0 here, which is a null. And then we specify the address of y to store the remainder of 7 divided by 5, basically. So y should end up with a value of 2. Okay. So this is what we want to do, and let's go check out how we do it. So we have to do this in a reverse order, which means the first thing we push is the address of y, because we have to prepare for the last or the outer div. So we first want to push the address of y. Well, guess what? The stack pointer is pointing to y at this point. So what we want to do is to push the stack pointer itself on the stack. Okay. Well, how do we do it? Well, kind of the same thing that we do for everything else, except this one is a little bit tricky because we have to take a snapshot of the stack pointer first. So I'm going to use C and say C points to y at this point because the stack pointer is pointing to y. And then what we do is we decrement D. We cannot avoid this because we have to allocate that space on stack first. Then we do stdc. So we are pushing the address of y on the stack. After that, we want to perform the nested call to div. Okay, so this one is just setting up 0, 3, and 15 on stack. So we do LDI. Since we're using C already, might as well use C. Okay, so we load immediate 0 into C, decrement D, stdc, LDIC3. This is the divisor for the nested call. Decrement D, stdc, and then we have the first parameter, which is 15. Okay, decrement D, stdc. So now we push 15 on the stack, and then we need to load C with the return address. So main return address 1, which is defined here. Okay, and then do the same thing. We do a decrement D, stdc. So now we have the return address push on stack 2. And at this point, it is time to call the subroutine or continue execution in the subroutine, which is div. When we come back at this point, we have 3 parameters still on the stack. So it is a good thing to deallocate those. Increment D, increment D 3 times to deallocate all 3 things on the stack. And in this case, it is required because otherwise those things will be still on the stack and interfere with the outer call to div. So at this point, we are now going to push 7 on the stack. Oh, wait, because the return value of the inner div is in register A, we need to push that on the stack. So we decrement D again, and then we do st D with A. So we are pushing the return value of div, I think it's 1530. So we're pushing the return value of this, which should be 5, on the stack. And then we push, okay, let me make this a little bit taller so we can see more code. Uh-oh. Okay, I guess, it doesn't show this window. It only tracks the browser behind it. Okay, so we have a little bit of a problem here because it's not tracking it's not tracking the terminal that is that is not it. UK. I'm just want to find out how we can, because all you can see is the window behind what I want you to see. Okay, so probably I have to re-record this, unfortunately. Hmm. I'm just checking out what I can do. Nope, that's not it either. Yep, that's the window that I want you to see. Unfortunately, okay, let me show you this part. Click OK. So this is the window I want you to see, but it's not showing that. It seems like I don't have the ability to only display a portion of the screen. So let me stop this streaming first, and then when I figure out how to do this, I'll do it again, or maybe I'll just upload the code so you can examine the code, in your leisure. So I'm gonna stop.